Hello to everyone and welcome to this Amatech Land webinar. Right now I'd like to introduce today's presenter, Manfred Heik. Manfred is the Global Infrared Product Manager at Amatech Land. With a degree in physical engineering, specializing in laser technology and optical metrology, Manfred has over 20 years of technical, product and application development, and sales support experience in optical and infrared metrologies. He focuses on developing Amatech Land's full range of non-contact temperature measurement products, including process thermal imagers. So Manfred, welcome to today's event. And with that, I'm going to pass things over to you to get us started. So go right ahead.
Welcome to this webinar discussing the improved process efficiency, monitoring and control with continuous high-resolution thermal imaging in industrial furnaces and boilers. Please let me shortly introduce myself. My name is Manfred Heik. I'm the Global Manager for infrared products like pyrometers, thermal imagers, scanners and systems used for advanced non-contact temperature measurement and controlling. While I work in the field of infrared metrology since more than 20 years, and mainly in the field of non-contact temperature measurement, I'm with Amatech Land since 2016. Please use my email address to get in contact with me. A copy of this webinar will be presented for review soon. This is what I would like to discuss during this webinar in more detail. The importance of continuous thermal imaging temperature measurement in process monitoring and control applications. The fundamentals of high-definition thermal imaging and its use in large furnaces and boilers. The challenges and solutions of obtaining wide furnace coverage of assets and stock. The energy savings plus efficiency and quality improvements achievable by accurately monitoring temperatures. Thermal imaging systems for continuous monitoring in different furnace and boiler applications. And last but not least, questions and answers. Okay, starting with the importance of continuous thermal imaging temperature measurement in process monitoring and control applications. In nearly all industrial processing or heat treatment applications, the process and part temperatures are one of the most important parameters to be measured and used to control the processes. It is not uncommon that the temperature is the only parameter which can be measured to control the furnaces. Additionally, the object and process temperatures are captured as a product quality parameter too. Especially regarding furnaces and boilers, with controlling the temperature in narrow temperature windows, the process efficiency increases and the fuel and energy consumptions decreases, while the emission decreases too. With increasing product quality requirements, a narrow temperature window must be guaranteed to reach the desired product and process quality. While traditional temperature measuring methods like thermocouples used in many industrial furnaces, these deliver the temperature at the location of the tip of the thermocouples. For example, the furnace atmosphere temperature. But they don't measure the direct product or stock temperature being heated, heat treated, or burned in the furnaces and boilers. There is of course an enormous variety of different furnaces and boilers present, and each of them are different to each other. These are only some examples for applications. Heating for hot forming like rolling, forging or banding, or reheating for semi-finished products like hot rolling, forging or mounting. Heat treatment for coating like galvanizing or galvannealing. Annealing processes like soaking, petrochemical processes like reformer and cracker, Incineration, like waste, coal, biomass. Carbon black, like black carbon, for example, for rubber production, and many, many more. A big amount of these furnace and boiler processes are fired by natural gas, but also can burn oil or other fossil fuels, creating complete different furnace atmospheres and measuring conditions. Special challenges require special measurement solutions to provide a full 24/7 view into the furnace processes and a continuous temperature measurement and controlling. Later, I will talk about special spectral responses of the furnace camera systems, challenges and solutions, and options like different auto retraction systems. Based on thermocouples penetrating through the furnace walls or roofs, or even temperature data loggers running through the furnace with the products, computer-calculated models are used to simulate the thermal processes and the stock temperatures. While these models are still an estimation, even a good estimation, they are based on indirect measurements mainly taken from thermocouple readings. Additionally, over the time, thermocouples can drift and need to be exchanged, or if they are damaged, they only can be exchanged at the next furnace renewing process. The main benefit of advanced thermal imaging furnace camera systems is that these measure directly into the furnaces and boilers, detecting the product and stock temperatures and distributions. At the same time, they measure the furnace walls, elements, and conditions. For example, like detecting leaks or critical hot spots or complex furnace temperature profiles, like in glass melt furnaces. Advanced thermal imaging in these furnaces and boilers enables to continuously monitor, visualize, and measure temperatures 24/7. Talking about the fundamentals of high-definition thermal imaging and its use in large furnaces and boilers. Discussing resolution of high-definition thermal imaging cameras and systems in some more detail. All of you will be aware of resolution in terms of amount of pixels of a camera or camera sensor, like it is discussed and advertised for smartphone cameras. These cameras are obviously visible cameras, and if the light intensity of the scene is less, the image will be electrically amplified and digitally optimized to get the best picture result. Apart from the small optic and aperture used with these kind of smartphone cameras, these cameras cannot be used to measure temperatures accurately. Besides the pixel resolution of a thermal imaging camera or detector, the thermal resolution is an important parameter which describes the basic noise level of such a camera and which smallest temperature differences can be detected as real temperature changes. It is called NETD, Noise Equivalent Temperature Difference, and is mostly of interest in low temperature, low signal intensity applications. With higher temperatures, the radiation and signal intensity is rising very fast, following the Stefan Boltzmann law. At higher temperatures, the noise level of such a camera system is dramatically lower than the measuring signal strength, which makes the noise negligible. Regarding the pixel resolution of high-definition thermal imaging cameras and systems, compared to TV formats, 16:9 is a pretty common ratio for TV formats. There are several TV resolutions available, like SDTV, HDTV, UHDTV 1 or 2, with its increasing amount of pixels. See left-hand side graph. Thermal imaging formats are usually based on a 4:3 ratio, providing different pixels amounts and different horizontal and vertical pixels. Proven cameras and systems like the ARC camera providing 384 times 288 pixels, so around 111,000 pixels, compared to the SD-TV format, 640 times 480 pixel resolution cameras are available with more than 300,000 pixels, or even cameras with extended resolutions of 656 times 494 pixels, so 324,000 pixels. With very high resolution and high definition camera systems provided with the 2K models like the Nearby 2K. These cameras provide a resolution of 1968 times 1472 pixels, corresponding to nearly 3 million camera pixels and temperature measuring points. Just remember, you might need to use 3 million parameters to create such a complete high-definition thermal image. As discussed previously, with visible cameras like smartphone cameras, the highest amount of pixels seems to be the most important parameter. But it is also a question how big you want to enlarge or print such a digital photo or picture later on. Compared to high-definition thermal imaging camera systems, different pixel resolutions are available and being aligned to specific furnace or boiler applications. 3 million pixel cameras are perfect, for example, for big furnace scenes, like big glass melt tanks, to provide a very high detailed image and temperature pixel resolution to monitor even small details at bigger distances. All these furnace camera systems are fully radiometrically calibrated. This means each of the 3 million pixels is calibrated to deliver a highly accurate and absolute temperature reading at each position of the thermal image. A choice of high-quality optics and field of views are available for different camera positions in different furnace or boiler applications, providing a homogeneous view across the whole thermal image. Basically, you can say the bigger the furnace, the higher the camera pixel resolution should be. Taking a deeper view into a high-definition thermal imaging camera application, like a big glass melt tank, see real images from a thermal imaging camera in this kind of application on the right-hand side. While the whole image of the Nearby 2K glass camera system used in this example is very detailed, clear and sharp, a digital zoom into the image is easily possible. With this digital zoom option, no temperature readings are affected, but the zoomed image scene is enlarged and shows this area very highly detailed. This enables the operator to inspect all areas of the furnace scene within the field of the view of the camera used at each time. With this high image quality, defects, leaks, or hot or cold spots can be located exactly and repaired to prevent further damage and energy wasting. These high-definition cameras provide not only an exact temperature measurement, even through hot combustion gases, but also a very clear, visible view for the furnace operators 24/7. In very big furnaces, like tube furnaces, sometimes not only the hottest reaction zone in a cracker or reformer furnace should be monitored, but also most of the environment in the furnace atmosphere. In these cases, usually several furnace cameras are used, combined in a camera system, and monitored by one thermal imaging workstation and software. Up to 16 cameras can be monitored and controlled with just one central workstation. With these specific application requests, our engineering team usually asks for dimensions and drawings or 3D drawings to plan and simulate the best camera locations and to monitor the whole area of interest. Remember, in these kind of applications, the operators are enabled to monitor and control the whole furnace process just from the operator room or via the company network 24/7 without the need to be on site. This is not only a big benefit for controlling a furnace or boiler process, but also taking out the risk for any people working directly on-site these hot or even hazardous areas furnace environments. While the field of view of a point measurement like a pyrometer is usually given in a ratio like 200:1, which means the spot size in a certain distance. The field of view of a thermal imager describes the whole image and pixel size in a certain distance. These are the main specifications describing the camera optics and image sizes. The horizontal field of view is given in degree opening angle in horizontal direction, for example 90 degrees. The vertical field of view is given in degree opening angle in vertical direction, for example 67.5 degrees. And the instantaneous field of view is usually given in millirad and gives a size of just 1 pixel depending from the distance. It can easily be calculated by multiplying the instantaneous field of view in millirad value with the distance in meter. The image and pixel sizes are usually given for different distances in each field of view table in the camera datasheets. The table shows an example for the NIRBI 2K 3 million pixel furnace monitoring camera system. Talking about optics. This is of course very important, especially with high-definition camera systems. As discussed previously, smartphones, for example, usually have pretty small lenses and apertures. They produce good images when there is enough light available and these images are digitally optimized. For measuring temperatures reliable and accurate, you need to collect enough infrared radiation energy to get a sufficient measuring signal and a low noise level. This isn't necessarily given with all thermal images in the market, especially the non-industrial ones. To provide a high-resolution and very clear non-disturbed image, besides the detector and the camera electronics, the optics plays a very important role. All AMATEC lens imaging optics are optimized to get the best result in terms of the MTF, the modulation transfer function. It describes the contrast resolution of an optic. See the image 1, showing a good and a bad MTF specification. The vignetting. Even with a digital camera, you don't want to have images which are vignetted in the image edges. See illustration 2. This is also an effect of the optic size and the free aperture. The image needs to be smaller than the optic aperture, which leads to bigger optic apertures. And the distortion can influence the image. If the optic is not optimized or too small, you might run into these distortion issues. See illustration 3. That's why the AMATEC lens cameras have an improved optic to ensure high-quality measurements and images based on more than 20 years of thermal imaging experience and knowledge. Additionally, there is another difference to non-furnace thermal imaging, for example, monitoring a hot object in a usual industrial environment, to thermal imaging into furnaces and boilers. Usually, with non-furnace applications, Approximately the half or even 3/4 of the whole thermal image is showing the hot object in front of a cold background. While the whole image size of a furnace thermal imaging system is covered with a hot furnace and furnace stock scene, this is of course an important difference and challenge to such furnace images. Providing most accurate temperature readings and a clear image, these furnace thermal imaging systems need a special radiometric calibration to deliver an accurate and homogeneous temperature reading across the whole thermal image, including the edges. All these thermal images are precisely calibrated to deliver very high reading accuracy and homogeneity throughout the whole image, even in very hot furnace applications and conditions. It is ensured that at each camera pixel, the correct absolute temperature is measured. This is documented in an extended calibration certificate coming with thermal imaging cameras and systems. Furnace and boiler imaging systems are designed for continuous 24/7 monitoring. All these furnace camera systems are water-cooled and air-purged to enable them to deliver high-quality measuring and monitoring results continuously. Existing vortex air cooling systems are typically limited in the operating temperature and cannot be used continuously in such hot furnace applications. Furnace camera systems are more than systems, consisting of borescope camera system included in cooling and protection enclosures, the air-purged borescope lens optic, a terminal box for powering and connecting the camera unit, and the Ethernet connection to the PC workstation for longer distances via light fiber data transfer. As an option, electrical or pneumatic auto-retraction systems are available to auto-retract and protect the thermal imager from damage by overheating in the event of loss of water flow, air pressure, electricity supply, or high borescope dip temperature alarm. These systems drive the camera complete out of the furnace area to a safe position where it easily can be inspected and maintained. As such, furnace and boiler monitoring systems are typically designed with borescope or lens optics. The tip of the borescope optic is exposed continuously to the hot and dusty furnace atmosphere. With the water cooling and air purging, they even withstand furnace temperatures higher than 1600 degrees Celsius. To protect the camera tip and the system itself to be overheated or even damaged, it will be retracted to a safe position in case of water, air purging, or power loss. An additional mechanical shutter separates the furnace atmosphere in front of the camera opening hole from the outside. These are very safe systems, working reliable in many furnace and boiler applications globally. Auto retraction systems are an option available for nearly each furnace camera systems. What are the main challenges and what are the solutions of obtaining wide furnace coverage of assets and stock? Most of the furnaces are fired with different fuels, which creates not only hot furnace atmospheres, but also different furnace atmospheres to the air ambient we are used to. So one of the most important challenges, obtaining a clear image and the correct temperature reading in furnace and boiler applications, is to understand the actual gas combinations and concentrations. See the below spectral transmissions for left, usual air atmosphere, and right, an example of an HPI furnace atmosphere. You can clearly see that the three transmission wavelengths are pretty different to usual air. This means that the absorption behavior of the furnace gases are different, and in addition, they can change with the gas temperatures as well. All these effects and influences need to be considered while selecting the best furnace camera system for a specific application. As an example, please see the right-hand side real thermal images, showing the same scene at different spectral camera responses. A shiny yellow flame is present during this measurement. While you see the flame using a 1 micron thermal imager, using the 3.9 thermal imager, you get a clear view while the flame is still present. This shows the effect of different furnace atmospheric gases and concentrations pretty clear. Following up on the former foil, depending on the fuel burned or the material incinerated, like in waste or biomass incinerators, it is essential to select the right spectral response and camera system for dedicated applications. These right-hand side images show a visible image of a waste incinerator and a thermal image into a biomass incinerator as examples. Another important challenge to be considered is the so-called background radiation. Usually in industrial furnace applications, the background, which usually is the furnace refractory or hot furnace parts like burners, are hotter or even much hotter than the stock itself. While each material and surface reflects a part of this background radiation or heat radiation, a thermal imager detects the direct emitted radiation of the hot object to be measured, and in addition, a part of the background temperature of the hot refractory. The right-hand side pictures show a visible view into a tube furnace. While in the inside of the tube furnace, an exothermic process is running, these tubes are much colder than the surrounding refractory. The below thermal image of such a tube furnace shows the exact and lower tube surface temperatures, including some critical hotspots, while the background or the refractory is about 300 degrees hotter. In this kind of furnace applications, the camera system, together with the advanced thermal imaging software, the Image Pro, automatically corrects the background temperature from the tube furnace temperature reading to get real tube furnace temperatures online. These images are taken within NIRB 643XR hazardous area certified furnace camera system and a tube furnace application. As already discussed, parameters or thermal images measuring into a furnace scene typically measure the direct emitted radiation temperatures and the reflected temperature from the background. See a principal behavior in the upper left-hand side graph. To correctly determine the object and stock temperatures, the correct surface emissivity of the stock to be measured need to be known. In many applications, like tubes and tube furnaces, it is not possible to even touch or measure the surface emissivity, as these hot tubes are in the furnace. To determine the right emissivity, so-called gold cup parameters are used, which use a hemisphere as a reflecting unit to select all radiation energy from the object surface in just one point, so the mirror center, while the background radiation is nearly completely blocked. This results in a nearly 100% emissivity and an exact temperature reading. Comparing this reading with a thermal imager at the same point, the correct emissivity can be determined easily. With actual Armatec land thermal imaging camera systems, a background compensation is done automatically and continuously. This in situ background correction is patented by Armatec land. With big temperature differences in furnace scenes, like with tube furnaces, the operator still want to get most accurate temperature readings even of the coldest tubes and the hottest areas like the burner zones of the furnace. This is a challenge with standard thermal imaging cameras too. The WDR technology, Wide Dynamic Range, allows the specific furnace camera systems, like the Nearby 640, to measure both the coldest and the hottest temperatures at the same time and with the same high reading accuracy. This is a big advantage for furnace applications where cold stock is running into or where colder parts are present in the furnace scenes, like with exothermic reactions. All these camera systems provide a continuous 24/7 monitoring and temperature measurement. As I already mentioned, there are some furnace applications which are hazardous area operations, such as tube furnaces, crackers, or reformers. To install a furnace camera system in this kind of applications, a hazardous area certified camera system is necessary. The Nearby 643XR is a certified system to be used in global hazardous areas applications. Get in contact with our engineering and sales team for more details. Why are these furnace cameras used, apart from temperature monitoring and visualizing? Let's talk about energy savings plus efficiency and quality improvements achievable by accurately monitoring temperatures. Even a 5-degree temperature difference can cause a huge energy wasting or even saving. Maintaining the correct temperature level and the temperature windows, it is an important task in controlling a furnace process. Based on predictive maintenance, long-time trending, optimization, and preventing failure and damage, maintaining the correct temperature levels and distributions in the furnace and at the stock ensures high-quality products results while minimizing energy, fuel consumption, and emissions. Such monitoring and trending can help to predict a special furnace behavior or even an upcoming issue of damage and enable the operator to fix these issues before a costly and critical situation might rise. The advanced thermal imaging software helps to clearly visualize and trend these temperatures, furnaces, and process changes. Another example: heating furnaces bring cold stock to the correct process temperature for forming, forging, or heat treatment. The temperature should be uniform throughout the product. This requires accurate temperature monitoring too. Temperature measurements are also key to providing optimized heating processes. For maximum energy and fuel efficiency, stock should achieve desired temperature shortly before discharge. If the stock is heated too quickly, energy is wasted and costs increase, and the properties and the surface of the stock can be affected. Heating needs to be uniform to ensure the entire product is at the correct temperature. For example, in forging processes, to prevent damaging the forging tool and negatively affect the forging and product quality. Furnace thermal images can help to provide this temperature and process control. I would like to highlight another advantage using high-definition furnace thermal imaging systems. These images are effectively working like two camera systems at the same time, one visible camera and one thermal imaging camera system. So why? Basically, the thermal imager is a camera, like a visible furnace camera too. But in addition to the clear image, thermal images provide a full radiometric temperature reading at each camera pixel. Using the same camera image, see the pictures. Even a black and white picture has the same quality like a pure visible furnace camera. So again, just one camera for both visible monitoring, and thermal imaging. This is obviously a huge advantage in using high-definition furnace thermal imaging cameras and systems. Discussing the last topic for this webinar, thermal imaging systems for continuous monitoring in different furnace and boiler applications. Some examples. These are some of the actually existing furnace thermal imaging systems. Each of these is provided for special furnace applications, like the Nearby 656 for medium and small furnaces, like cement furnaces, rotary kilns, or even boilers. The Nearby 2K for large furnaces, like big glass melt tanks. The Nearby 640 with WDR technology for heat treatment and reheat furnaces. And the Nearby 3XR, which is hazardous area certified for tube furnaces in the HPI industry, for example, reformers and crackers. All these cameras are available with different versions, providing the best solution for each furnace monitoring application. In hot or even very hot furnace applications, the use of an outer retraction system is recommended. Electrical and pneumatical systems are available for all non-hazardous area certified borescope camera systems. Different length of the probe, so the borescope optics, and retraction systems are available to penetrate the furnace wall. For hazardous areas, a fixed installed system is used, as moving mechanical parts are not allowed in this area. This drawing is taken out of the actual installation guide for the electrical outer retraction system and shows all components in more detail. While the camera in a standalone solution is directly connected to the ECB Ethernet connection box and the PSU power supply unit, using the electrical outer retraction system, the camera is connected to the outer retraction system, which is then connected to the field connection box and media supplies. On the right-hand side of this foil, these two images show a borescope camera mounted on an electrical outer retraction system at the retraction position and at the measuring operation position. Thank you for your attention and interest in improving process efficiency, monitoring, and controlling with continuous high-resolution thermal imaging in industrial furnaces and boilers. During this webinar, we already received some questions I would like to answer with the following points. The first question is, can every camera system being used with an outer retraction system? Well, as discussed, there are two kinds of retraction systems available, a pneumatical and an electrical outer retraction system. While the electrical outer retraction system can be used with all camera systems except the hazardous area, the pneumatic outer retraction systems are available for the glass furnace camera models only, like the Nearby 656 glass and the Nearby 2K glass. On the right-hand side, you can see a table which gives an overview which outer retraction systems are available for which camera systems. Next question. Does a higher pixel resolution camera has a higher temperature reading accuracy? The basic answer is no. While typically the size of each camera pixel at the detector plane gets smaller with increasing amount of pixels, the sensitivity of each pixel usually is higher too. The signal-to-noise ratio mainly depends from the high-quality electronics used in these kind of camera systems. At higher temperatures, the signal power or radiation power increases dramatically, which results in a high and stable signal to be used to measure temperatures most accurately. Next question is it necessary to calibrate the camera system on a regular basis? Well, it is recommended to check and calibrate all thermal images every 1 to 3 years, depending on the instrument and the application environment. While semiconductor detectors are very stable, thermal detectors require a NUC, a non-uniformity correction, on a regular basis, for example each 90 seconds, which homogenizes the whole image and is done automatically with the camera. While in some applications an accurate absolute temperature measurement is required, in some furnace application only monitoring applications like coal boiler or slag monitoring, it is a relative temperature measurement, detecting contrasts. In case of a calibration or fail, the Armor Care service offering provides a spare camera in case of service repair on a global base. Next, which software is used with the borescope camera systems? In industrial thermal imaging applications, and of course in furnace monitoring applications, a dedicated software is needed to visualize, analyze, and capture temperatures and to control the whole furnace process. Based on the Image Pro advanced thermal imaging and processing software packages, the furnace process can be controlled and monitored while the temperature data and distribution is analyzed and captured online. For specific applications like the glass industry, special application dedicated software packages are available too. An important question is, what are the main parameters to select the best camera system? What is the process temperature? Mainly the lowest and highest temperatures are important parameters. What is the fuel the furnace is burning in order to determine the best spectral response? What is the size of the furnace and the size of the area to be observed in order to determine the best pixel resolution and optics? What are the environmental conditions in order to determine if a retraction system is needed? Is it a hazardous area environmental in order to determine special hazardous area certified camera systems? Finally, we are now through this webinar, and I hope you enjoyed this webinar and you learned some new and interesting things. As every time more questions coming up, I think so, please give us an email or a call and our engineers will be happy to answer your questions in detail. All global contacts you can find on our webpage, amatec-land.com. Thank you for your attention.
Okay, Manfred, thanks so much for that great presentation. Now we're going to wrap things up right there, and we'd like to remind everyone to reach out to Manfred or go to Amatec Land's website if you have any further questions. Take care and have yourselves a great day.